start with the tracking problem in state feedback design part 2. In this we will study design of state feedback controller considering integral control and numerical examples. Now about the design of state feedback controller considering an integral controller. In classical control aspects, the different controllers have been used, particularly proportional controller, proportional integral controller, proportional integral derivative controller, sometimes PD controller. The main role of derivative control is to reduce the overshoot. The main role of integral control is to reduce the steady state error. And now we have seen that in our problem of state feedback control design, there is a issue of steady state error. So now in classical control there is a proportional integral which reduces the steady state error, and in our advanced control there is a issue. So can we combine the classical approach of PI with state feedback design? So it is possible that if we use the concept of proportional integral in a state feedback design, we can get the reduced steady state, or we can say we can't get any steady state error, that is the output track the reference input properly. So here we will see how we combine the proportional integral aspects in state feedback controller design. As our plant is x dot equal to Ax plus Bu, y equal to Cx. Now the block diagram for this, here is summing block, here is one integrator, now here output C, this is C and here Y, and here is we have A matrix, this Ax, now here is B matrix, now here is U, and here control law, we have control law U equal to minus Kcx plus R. Therefore here we are going for our control law U equal to Kcx plus R. Now here we have a controller Kc and here is x. So U equal to minus, that means this R will come into picture. So this is our conventional approach, that is if you connect R here, that is U equal to, this is say minus Kc plus R, and here is x dot equals to Ax plus Bu, y equals to Cx. So by conventional approach we will get this type of block diagram, but there is a issue with the steady state error. Previously we have seen that adding a certain block here, that is we have seen that adding one block of Ts, and finally we have determined Ts in order to get the zero steady state error, or in order to track the reference input, that we have seen. Now here some idea of integral concept we have to use. Therefore here what we are doing here, we have add another block K, that is a minus Ka, and here is we add one integrator, and here is state say xa. Now here is xa dot, and here is another summation block. Now here is your R, and now here is so now here this particular block diagram, this particular portion this particular portion is resemble to advanced control state space, and this integrator of XA, this resembled to our integral controller issues. This integrator means one bias that reduces the steady state error, and now you see the concept that how to reduce the steady state error by means of this one, but now here the control law equals to minus Kx plus R. This is earlier law. Now here because of this your control law will be modified. So here the control law is u equal to minus Kc into x minus Ka into Xa. So you see that this control law u equal to minus Kc into x, this is x, minus this is Ka into Xa. Now here two types of variable x and Xa, and we will find that because of this arrangement definitely the number of state has been increased. Now we will see the state equation as x dot equal to Ax plus Bu. This is the state equation for the original plant, and because a new state has come, so here the equation is Xa dot equal to R minus Cx. You will find that here Xa dot equal to R minus Y, that is here this Xa dot equal to R minus here Y, here R, Y is C into X. Therefore here we got X and Xa dot, and if you combine this equation X dot Xa dot here A 0 minus C 0, that is x, here is Xa plus B 0 into U plus 0 1 into R. So this is the state space model of a system when the integral controller has been included in the state space model. Now here this is the complete system. Now here our control law is also changed, because earlier our control law is u equal to minus Kx plus R, that is Kcx plus R, but now here our control law has been changed to minus Kcx minus Ka into Xa. This is our control law. That means your control law in this case is u equal to minus Kc into x minus Ka into Xa. So this is the control law, u equal to minus Kcx minus Ka into Xa. This is the control law, and now you have to use this equation here and then solve it, and finally you will get the compensated system as so our compensated system is x dot Xa dot, that is A minus B into Kc minus B into Ka minus C 0 x Xa plus 0 1 into R and y equal to 1 0 0 x. Because of this new control law and this state space model, we will get the compensated system like this. And now in order to simplify the result, because our final aim is to reduce the steady state error, or your output must track the reference input, error to be 0. Now, in order to see this, we will take this block as say A1. Now, this block say as B1, and here this block as is C1. So, here the state space model is steady state equal to x dot equal to A1 XSS plus B1 into R y equal to C1 into XSS. That means earlier which we have taken. So, actually this B is the involvement of 0 0 say 1, just like this, because as if this is increase the order, we can get more elements. If the second order plot is there, we can across 0 0 1. So, here output is we can say 1 0 0, as assuming that the plant is of second order, or if for simplicity we can say that this is particularly only C1, B1 and A1 only. So, here we come across xs dot equals to A1 XSS B1 into R y equals to C1 into XSS. Now, what at steady state, at steady state where x s dot equal to 0. So, x s dot equals to 0, therefore, this x s s dot equal to A1 x s s plus B1 into R, though this is equal to 0. So, 0 A1 x s s plus B1 into R, that means here we can write x s equal to minus B1 into R and y s s equal to minus C1 A1 inverse this B1 into R. Now, here we will find that we have compensation system ABC, now x x a, now here 0 0 1. So, if the order is 2, this for original plant is 2, then is 0 0 1 and output is correspond to 1 0 0. So, that is we can say is C1 we are written. So, here xs dot A1 xs B1 R y equals C1 xs. Now, assuming that these or we can say consider that this is for nth order, and therefore, at steady state xs dot equals to 0. So, xs dot equals to A1 xs plus B1 into R. So, 0 A1 xs plus B1 into R. So, we got y ss equals to C1 into B1 into R. Now, about the steady state error ESS is given as R minus YSS. So, here we can write down as R plus C1 A1 inverse B1 into R, and here we take R as common, we will get 1 plus C1 A1 inverse B1 equal to 0. So, here steady state error is to be 0. So, when this is possible? So, this is possible when this is the condition C1 A1 inverse B1 equal to minus 1. So, this is the conditions. So, when these conditions comes, then we can say that steady state error equals 0. Therefore, whenever problem is given to you, in that case you have to determine the C1, you have to determine the A1, then take A inverse and B1. If it comes minus 1, it means that means the result of this is say minus 1, it means that we have got 0 steady state error, that is output tracks the reference input correctly. Now, we solve the example to see whether we get the 0 steady state error or not. Now, about the numerical examples, now we see the double integrator problem. For double integrator system, double integrator means that there are two poles at the origin, that is your g of s equal to 1 by square. Now, our main purpose is to design the controller for this plant. Along with that, we had to reduce the steady state error as GS equals to 1 by square, that is the order of the system is 2. And now here we are designing control using state space, that means the maximum states in this case is 2, just looking after the problem. Now therefore first aim is to develop the state space model of this double integrator. For state space model, we had a GS equal to 1 by square, the order of this system is 2. So order is 2, it means that number of states are 2. And if you want to write the state space model of such type of equations, in that case we have to write like this: x dot equal to 0 1, because now here we are writing down the equation in a companion form. The arrangement is 0 1 and we have to write the elements of the denominator. Now here the elements of s square. So when we write the companion form through the transfer function, there is no need to take the elements of this, we have to take the remaining elements here. So the remaining elements in the 1 by s square is 0, therefore we can write down as 0 0, and here we write down as x plus 0 1 into u y equal to 1 0. So this is the state space model of a double integrator system. Now here we have to design a controller. So the number of states are 2, and because of the integral controller, one state has been added. That means if you see this one, so this is resemble to your C1 matrix which you are taken, and here B is supposed to 0 0 1. Now here what we can do, here we write the given system as x dot xa dot as a minus b into kc minus b into k into a minus c equal to 0 x xa. Now here 0 1 into r. So now here a b k c, and this is a k element is there. So if you write down the model of the system taking care of all the states, that means here taking care of this x xa dot a 0 c 0 x xa b 0 0 1, that is this is the particular the model of the system when we added integral controller. Now in this problem what we have to do, we have to write the elements of a, elements of c, x xa b 0, and we see the equations. As the model is x dot xa dot 0 1 0 0 0 0 minus 1 0 0, here is x xa 0 1 0 u, and here 0 0 0 1 into r. This is the state space model of the system when there is we can say no controller, and we have got these results. The xa dot is the part of the integral controller. Now our purpose is to design a controller. Suppose our pole placement we are defined or minus 1, minus 2, minus 3. So this indicate your desired poles. So in the desired port we have taken minus 1, minus 2, minus 3, all are real ports. That means in the performance there will be no transients involved. So As we have seen the formula earlier, the controller Kc equal to 0, 0, 1 controller by T inverse Qc inverse into phi of A. So, if you use this formula, you will get the result as the controller Kc will get as 11 6 minus 6. The first part 11 6 is corresponding to the part of the original model, and minus 6 is corresponding to another XA. That means every state there is a controller again. So, 11 and 6 for original state and minus 6 for, we can say, for XA variable. Now, as we have seen, this is a compensator system. So, this compensator system for all these values we can write down as x dot XA dot 0 1 0 minus 11 minus 6 6 minus 1 0 0. Here is x XA 0 0 1 into R, and her output 1 0 0 0 x into XA. Now, this is our compensated system, and in the compensated system we take this as A1, this as B1, and this is as C1. So, A1, B1 and C1 are there, and we have seen the conditions. The condition for steady state error to be 0 is C1 A1 inverse into B1, that must come as minus 1. So, here the condition for steady state error, so YSS equal to minus C1 A1 inverse B1 into R. So, you will find that this condition is satisfied. Here will come as minus 1, as I have seen, minus 1 C1 A1 into B1, and here we will get YSS equal to 1, and the steady state error ESS equal to 1 minus 1 equals 0. So, replacing all the values of C1, E1, B1, we will get steady state error as 1, and ESS equal to 1, reference input 1 minus 1 equal 0. That means the conditions of the steady state error to be 0 is satisfied. Now, we see another example. Now, we see the example which we had taken last time, particularly related to the compensating factor part, that is x dot equals to ax plus bu, y equal to cx. Now, here A matrix is say 0 1 minus 9 minus 1, and here B equal to 0 1, and here C is 1 0. Now, here we have x XA dot. Now, here using this formula, this one, using this formula we have to determine the compensated system, and for that purpose, for this particular problem we take the case as the desired pole placement, say dp equal to say minus 1, minus 2, minus 5, and we have to determine the controller k. Finally, we get this as 8 7 minus 10. So, this 8 7 is corresponding to k, and this is corresponding to the additional state, that is a Kc, and this part is concerned with the Ka, and the composite system will get as 0 1 0 minus 9 minus 1 0 minus 1 0 0, this x XA, and here 0 1 0 to u, and here y equal to 1 0 0 here x into xa, and this is the particular the model of the plant, and here we get this final system in terms of composite model as x xa dot, that is equal to 0 1 0 minus 17 minus 18 10, here minus 1 0 0 to x to xa plus 0 0 1 into r, and here y equal to 1 0 0 into x by xa. Now here is our a1, here is b1, and here is our c1, and now if you solve this one, we can get YSS equal to minus c1, that is a1 inverse into b1. So particularly c1 a1 inverse. So if you use the values of a1 b1 and c1, we will find that we will get here minus, and here get this minus 1, here we will get minus 1, it is goes as 1. So steady state error or steady state output will comes to be 1, that means your the error steady state error ESS equal to R minus YSS, that is 1 minus 1, that is steady state error equal to 0. And so we will find that if you use the concept of integral aspect in a state space analysis, we have got the steady state error 0, that means output track the reference input properly. But here we find that the complexity in the calculation has been increased, because in earlier times we have seen that we had to design the controller for the minimum state. That means if you see the additional of part additional compensation, that is TS which we have taken, that is method 1. In this approach, the controller has been designed for the original plant, that means if for the second order system we have got controller Kc as here K1 K2, and final system has to deal with the second order. But if we consider the integral aspects, that means in that case we have to consider the state of that pole, that is the additional of the integrator, and therefore in that case your this Kc is nothing but this final controller Kc is equals to this Kc divided by into K. So this Kc is corresponding to two part, that is say your Kc1 and Kc2, and here is a Ka. That means the complexity has been increased, we have to take into account more state, but our error has been reduced. So as far as the stability issue is concerned, as we know that as the order increases there can be issue of the stability. Therefore the methodology which we have taken earlier, that is method 1, is quite better from the stability point of view, because in that case there is need to taken care of the minimum state. But whereas in this case, that is in case of the addition of integral, we have to consider more state. Therefore the method 1 is beneficial in comparison to other method. So now about the state space issues, we have designed we have developed the state space model, then we have designed a controller, then we have seen the issues relating to the tracking. Now there is also another issue about the states, because the state feedback design is possible when we can measure the states, but there may be possibility that sometimes we cannot measure the states. Then how to handle this? Because if you can't measure states, This is never be possible, because when state measurable, then controller design is possible, but when state can't measurable, this type of thing is never possible. Therefore, there must be some arrangement by which we can some estimate the state. So, that means the state observer. So, that part we will see in the next part. So, these are some references. Thank you.